Let's go through this review worksheet for the stoichiometry test. And believe me, you're going to do well on this test. Here we go. Now, the first couple of items on the worksheet were to make sure you could think about, oops, that's the wrong marker. Let's look at this. There we go. You could calculate things like percent yield and percent error. And percent yield, typically if you're working with a lab or a manufacturing process, and you go through the process and you get some material out at the end of your process, that is your actual results. Now, the theoretical results is based on a calculation that you would use of looking at all of the chemical reactions involved and doing a stoichiometry problem to determine the theoretical results. Now, the difference between percent error and percent yield is that in percent error, you're trying to see how far you are from the theoretical value and dividing that by the theoretical, so you see how far away you are from being 100%. And in calculating percent yield, you're also seeing how far away you are from 100%. And usually you'd expect your percent yield to be something a little less than 100% because you've lost some material along the way in the process. Now, there are many ways of describing how to determine a limiting reactant. The limiting reactant, keep in mind, is the reactant that runs out when you're carrying out a chemical reaction. So if you dump in a bucket of this and a bucket of that, you don't necessarily make two buckets of your product because some of that reactant isn't going to react. One of the things is going to run out first. So there are two ways outlined here, and you may want to read those and think about those a little bit. Pause the video if you need to do that. Problem 4 says to describe the steps in dimensional analysis, and you certainly can use something different than what I have written here. I was simply trying to do this following along, looking at a typical stoichiometry problem and the dimensional analysis involved there. So the first thing we have to have is a balanced equation and identify what we know and what we don't know in that balanced chemical equation. Now, I've chosen to use hydrogen and oxygen combining to make water, and that the known was the amount of oxygen, and the known is the amount of hydrogen in this problem, and the unknown the amount of oxygen. So the first step here is to convert the grams of what we know to moles of what we know. And we do that in such a way that the grams of hydrogen cancel out. And of course, this 2.02 comes from the molar mass of two hydrogens. We got that number from adding 1.01 plus 1.01, the molar mass of hydrogen on the periodic table. And the next step is to convert to moles of the unknown. You'll see that moles of unknown was oxygen. And we see that this mole ratio of 1 mole of oxygen to 2 moles of hydrogen, that comes from right here in our balanced chemical equation, the coefficients here in the balanced chemical equation. And then we convert the moles of unknown to grams of unknown, so that our final units are in grams of oxygen. We multiply everything on the top and divide by everything on the bottom, and you should try that just to make sure you understand how to make your calculator do that calculation, and you should get 4.46. What's question 5 about? Well, question 5 is just saying what is the minimum number of grams of CO2 needed. It's a straightforward stoichiometry problem. As you realize, what this is saying is that the glucose right here, the 1,000 kilograms of glucose, is going to go into making wood. And so it's going to take at least 1,000 kilograms of glucose to make 1,000 kilograms of wood. That's a big chunk of wood, weighs 2.5 tons or something like that. Excuse me, 2,500 pounds or something like that. So the unknown is to ask how much CO2 that's going to be, how much CO2 it will take to make 1,000 kilograms of glucose. So the first thing I did was convert kilograms to grams, and then we're going to convert grams of the known to moles of the known using the molar mass of glucose. Once again, this ratio of 6:1 comes from the balanced chemical equation. And 44.01 is the molar mass of glucose. How many sig figs here? Well, it depends on whether you consider 1,000, whether that had 1 sig fig or whether it intended to have a decimal point at the end. But the answer is either 1 million grams of CO2 or 1.466 times 10 to the 6 grams of CO2. So let's move on to number 6. Now when we look at number 6, we see, let me get my writing things back. Come on. Writing tools, there we go. We see that in this problem, we're starting with 5 grams of aluminum and 25 grams of dimethyl mercury. And the question is, I'm looking for the question. Calculate the mass of trimethyl aluminum that can be prepared. Well, we can't just say, well, I'm going to add 25 and 5 together and get 30 grams, and that's how much we're going to make. No, what we're going to look at is which reactant is going to limit what we can make. One of these is going to run out first, and the method I've chosen is to start with grams of aluminum and carry out a stoichiometry problem and see if we ran out of aluminum first, we would make 13.4 grams of the trimethyl aluminum. And if we run out of the 25 grams of dimethyl mercury first, we'd make 5.21 grams. Well, which one can we actually make? Well, we're going to run out of the dimethyl mercury after we have made 5.21 grams. So that is the amount we can make. We can only make, come on marker, we can only make 5.21 grams. Limiting reactant problem. Let's look at number 7 and see what it is asking. Number 7 is a straightforward stoichiometry problem as long as you know how to write the balanced chemical reaction. That's really the thing you have to be sure you can do here in this problem. If you don't have the balanced chemical reaction, you won't be able to do the stoichiometry right. Pause the video if you need to so that you can look over how we set up this problem, number 7. Moving on to problem number 8. Problem number 8 says, what is the percent yield? And so to calculate percent yield, the first thing we have to do is a stoichiometry problem to find the theoretical yield. That's problem number 1 here. And the second thing we have to do is do a calculation to find the percent yield. So keep in mind here that what we know is the 1.52 grams of potassium hydroxide, and the thing we are looking for, our unknown, is this theoretical yield, so that we can use this theoretical yield to calculate percent yield. Note, it's a good idea to carry extra significant figures until the end of the problem so that you don't have any rounding errors in the middle of your problem. That's the way to do it, is carry significant digits or additional digits to the significant digits on into the rest of the problem. And you should get 86.2% yield for this problem. Where did the actual yield come from? It came from right up here. Where is it? There it is. Actual yield, 1.10 grams of potassium oxide is formed when I did this reaction. That's what I actually got. Well, I only got 86.2% of what I should have gotten. So that's number 8. Good luck as you study for this test.